So let's talk about linear systems, right? So the idea is to solve linear systems. And again, a linear system, just to recap things a bit, it's nothing but a set of linear equations. And for the sake of this discussion, at least for now, we're going to limit ourselves to n by n systems, right? When I say n by n systems, I'm already talking in matrix terminology. What I mean is it has n rows and n columns, but in terms of linear systems, what I really mean is it has n equations. So there are n equations in n unknowns, right? And so for now, I'm just sticking with n by n systems. We'll look at systems where there's a disbalance between the number of equations and unknowns, but for now let's just limit our discussion to that. And in particular, we'll limit ourselves to the 2 by 2 systems or the 3 by 3 systems. Once we have a good idea of what's happening in a 2 by 2 system and a 3 by 3 system, we'll have basically all of the tools that we'll need to do not to visualize, but to at least solve n by n systems, where n can be 3, 4, 5, 6, 10, 100, 1000. Of course, as n increases, it becomes impractical to try to solve it on paper with a pen, but the tools are the same. You can solve it using some computer software, maybe MATLAB, and the idea is, even behind the codes that are written for MATLAB, the ideas of elimination still carry forward, and they are the same. So let's just start off by first looking at a system. And so here's a system of equations. The system is, let's say, x plus 3y plus 2z equals to minus 3, 2x plus 2y plus 2z is equals to minus 2, and 3x plus 5y plus 6z is equals to minus 5. Right? These are the set of equations that I have. Hello Anifa, thank you for joining. And so let's look at the system of equation, and the idea that we're going to discuss today is the process of elimination, right? And we perform elimination by getting rid of one variable, eliminating one variable per equation, right? And the way we do this is as follows. We start off from the second row, and so we first look at the first row and we see, okay, it has all of these three variables. It has x, it has y, it has z, and I'm going to look at the first coefficient and notice that there's no coefficient written, which is of course means that the coefficient is 1, and so that I'm going to call my first pivot. And using this first pivot, I will try to eliminate the x from the second equation and the x from the third equation. So I'm looking to do the following. I'm trying to think of multiply row 1, right? So I'm calling this row 1, or let's not do that. Let's call it equation 1, right? So this is equation 1, this is equation 2, and this is equation 3. So let's limit ourselves to the equation terminology for now. So multiply equation 1 by some number, right? And subtract, right? So please make sure that we're using the convention of subtraction here. Some books use the convention of addition, and that creates a sign issue. Our sign might be different from their sign, but that's fine. We'll just adjust our signs based on our discussion on subtraction, right? So we multiply equation 1 by some number and subtract it from equation 2, right? And so the way now I want to multiply this equation 1 by some number such that when I subtract that result from the second equation, I get 0 in the first equation. So I'm really looking for, so I'm trying to think of 2x. So let's say I multiply this number by let's call that multiplier m. So when I do the subtraction, 2x minus m times 1x, what I'm really looking for is 0, right? And now there's no need to make this equation, even though I can make it, there's no need to do it, but let's do this. So 2x minus mx is equals to 0, and I can immediately say that if this m were 2, I would have my answer. So this m multiplier needs to be 2. So later on I won't be making this equation, I'll just try to guess what this number should be, what this multiplier should be, right? So the multiplier in this case, so the multiplier is equals to 2. And so what I'm going to do now is I'm going to do equation 2 minus m times equation 1, right? And so what's the result that I get? So I get the first equation I leave untouched, x, so x plus 3y plus 2z, 3y plus 2z is equals to minus 3. The second equation becomes, so I'm going to do 2x minus 2 times this, so I'm going to go with each number, even though I can do something like 2x plus 2y. Maybe you can do something like this on the side, 2x plus 2y plus 2z is equals to minus 2. And what you have is you want to subtract minus 2 times, so when I multiply this equation by minus 2, I get minus 2x minus 6y minus 4z plus 6, right? So I get minus 2x. I'm just going to do it systematically for the first one, and then I'll stop using this terminology, right? So minus 3 minus 6y, and minus 2 is minus 2 times 2 is minus 4c is equals to 6, right? And so now I subtract this. Sorry, so the multiplier was 2, I was multiplying it, oops, I should have not changed the signs yet because I'm multiplying it by 2, not by minus 2. So this is minus, and now I want to subtract this. So if I want to subtract this equation from this equation, I change the sign. So minus, minus, this is plus first, this was plus, this was plus, and this was minus. And now I change the signs, minus, and this becomes plus. So 2x minus 2x becomes 0, 2y minus 6y becomes minus 4y, and then 2z minus 4z becomes minus 2z is equals to minus 2 plus 6 becomes 4. Okay, so that's the elimination that I'm looking to do. And so now once we have that process in our head, we don't need to keep doing that. We know how to do this. So I want to do 2x minus 2x is 0, 2y minus 6y is going to give me minus 4y. So let's plug that here, minus 4y, and the second term is going to be 2z minus 4z is going to give me minus 2z equals to, again, minus 2 plus 6 gives me 4. So that's my second equation, my new second equation, right? Okay, and let's do the same process for the third one. So now I want to multiply the first equation by something, so that when I subtract the result from the third equation, my x is eliminated. And this is obvious now that I need to multiply it by 3, so when I subtract it, it becomes 3x minus 3x. So 3x minus 3x is 0, I have that, let's ignore that. 5y minus 3 times 3y, so that's 5y minus 9y, so I get minus 4y again. And then 6z minus 3 times 2, so 6z minus 3 times 2 is, I believe, 6 minus 6, so that becomes 0. So I have no z here at least, so let's ignore that for now, is equals to, what I get over here is 6 times minus 5. So I have subtraction here, so over here I have minus 5 minus, and I was multiplying it by 3 and then minus 3, so just making sure I get the signs correct. So minus 5 plus 9, which means I get minus 4 over here, right? Okay, so these are my new 3 equations at this point, and at this point I can stop and I can really solve these equations, but let's stick with this method because it's not always going to be the fact that I get a 0 here and I can easily solve this equation. So I want to repeat the process and I want to eliminate. So I've eliminated x from, so in the first step I eliminated x from both of these, and now I want to eliminate y from equation 3, right? Okay, so this was my first pivot, this was going to be my second pivot, because I'm going to start from here. Notice that in the equations, new equation 2 and new equation 3, there is no x, so these are just two equations in y and z. The third equation is actually just an equation in y, but I'm going to stick with my method so that I have a general method that I can always use and not rely on the fact that this z becomes 0. Minus 5 plus, oops, yes, you're absolutely right, Tanya, this is 4. Okay, now at this point let's carry this forward. So I'm looking for some number to multiply this equation so that when I subtract this, it becomes 0. So immediately notice that if I do minus 4y minus 4y, this is minus 4 plus 4, which is immediately 0. So I don't need any multiplier. The multiplier is simply 1 at this case, right? So I just subtract equation. So let's call this 2 star and let's call this 3 star, and now I subtract 2 star from 3 star, and so the first equation remains as it is, x plus 3y plus 2z is equals to minus 3. The second equation is minus 4y minus 2z is equals to 4, and now let's do the subtraction. Minus 4 minus minus 4 is plus 4, so this becomes 0. So there is no y here. 0 minus minus 2z, which is plus 2z, so I get a 2z here, is equals to 4 minus 4, which is 0. So this is my new system of equations where I have 1, 2 and 3 pivots, right? So in the diagonal we see that there are 3 pivots, but I can of course stop now because there is no equation below this last pivot. We just have 3 equations, and so I can stop at this point. I have no more elimination to do. Okay, so at this point I have converted my system to a what I call a triangular system, and we call it triangular because notice that if I put this into matrix form, if I looked at the coefficients, I have 1, 3, 2, minus 4, minus 2, 2, and below this is all 0. And so schematically, if we think about it, this forms a triangle, right? And matrices such as this we call upper triangular matrices. So I'm making this triangle, so upper triangular matrix, right? And the good thing about upper triangular matrices is that in form of systems, they're incredibly easy to solve. So now if I want to solve this system has been essentially solved for me. I can use this equation to say z is equals to, let's shift this, and so this equation tells me that z is equals to 0. I have the value of variable z. I can go to this equation, substitute my value of z and find the value of y. So this equation tells me that minus 4y, c is 0, so that I get rid of that, 4, which means y is equals to minus 1, and finally y is minus 1, x is this, so x minus 3 plus 2, I don't need anything over here because z is 0, so 2 times 0 is 0, so this gets eliminated, is equals to minus 3, and now this goes to the other side, I get x is equals to 0. And so my solution x, y, z to this problem is simply 0 minus 1, 0. Okay. Yes, thank you, Danya. I think I've corrected the error and hopefully there's no error. Okay, there's two things to notice here. First, of course, the method of elimination gave us a result, and the reason that it was successfully able to give us a result was that we kept finding pivots. If we fail to find pivots, our method of elimination might face a setback, and we'll see what happens when we face a setback, right? The other thing to notice is I could have really simplified this entire process by ignoring x, y, and z, because nothing really happens to this x and this y and this z. They just hang around, and the only numbers that change are the coefficients and the right hand side. So I can showcase this entire method by saying, okay, this was my matrix, right? So let's look at this system. So I'm going to convert this method of elimination that I just did by, so this was my first system. I'm going to say that my matrix, the corresponding matrix form of this equation was 1, 3, 2, 2, minus 2, 2, 3, 5, 6. Is that correct? Yeah. Sorry, this is a plus. This is aligned over here. Okay. And I can also write the right hand side over here, right? So let's just put a little dashed bar here and minus 3, minus 2, minus 5, because these are the numbers that change. And this matrix, the matrix of this form, where I have not only written the coefficient matrix, but I've also sort of put the right hand side over here. This is called an augmented matrix, and I'm doing this because the right hand side also changes, so I want to keep track of those numbers, right? And so notice that when I did the first elimination, I got this matrix, right? I got this system. I can put this system over here, and instead of thinking about it in terms of equations, I can just do the process on the rows of this matrix. So I repeat the process and I say, okay, I want to get rid of, this was my pivot, this was 1, right? And I want to get rid of 2 and 3. So now I do row 2 minus 2 times row 1 of this matrix, and row 3 minus 3 times row 1 of this matrix. And what I get, if you notice that if I do this process on this one, then this is just 1, 3, 2, minus 3. And if I do row 2 minus 2 times row 1, then that's, of course, this is 0. This gives me minus 4. This gives me minus 2, and this gives me 4. Okay, and again, row 3 minus 3 times row 1 gives me 0 here, and minus 4 here, and 0 here, and 4 here, right? And so there's no reason for me to write these x, y's, and z's over and over again. I can just look at it in terms of matrices and make it convenient for me, right? Okay. And so now I do, again, I repeat the process, and I look at my last system, which was this one. This is the system that I got after eliminating the last variable, the y variable in the third equation. And so this system becomes this system, right? So this is 1, 3, 2, minus 3, and 4 here, minus 2, minus 4, 2, 0, and 0, 0, 0, right? So at this point you stop the process of elimination. So what I'm telling you is not to do the elimination on the equations. Make it easier for you, put it in a matrix form, and then do the elimination row by row, right? So first pivot, second pivot, and then third pivot. Okay, any questions so far? So when I wanted to go from this matrix to this matrix, I did row 3 minus row 2. Okay. All right. So let's think about this solution that we have. X, y, z is equals to 0, minus 1, 0. And at this point, I realize I didn't really need to solve this system, because the solution is telling me that if I had just looked at my system of equations a bit more carefully, I could have found this answer without really going through all of this mess, because the system of equations that I had at the start was a very nice system. And let's find out why it was so nice, right? And so let's put this over here and let's look at the column picture of this equation, right? And so here's my system. I can write it in matrix form by writing 1, 3, 2, 2, 2, 2, 3, 5, 6, and x, y, z is equals to minus 3, minus 2, minus 5. right? And now I want to switch to the column picture, which will tell me why I didn't need to do all of this mess, even though I'll need to do all of that computation in most of my systems. But when the solution is so simple, it might really be worth doing. We might, so let's look at the column picture. So instead of, or view it as a linear combination of, so AX as linear combination of columns, right? So here it is. So I write it as x times 1, 2, 3 plus y times 3 to 5 plus z times 2 to 6 is equals to minus 3, minus 2, minus 5. And so the question, let's change the question. The question, when you look at this linear combination, the question really is, what combination of these columns do I take to give me this column minus 3, minus 2, minus 5? And I want you to think about that problem while I look at the chat. And so Hamad says, can we do row 3 minus row 1? You can, so that's what I did, row 3 minus, so you should avoid, Hamad, the reason we don't do row 1 plus row 3 anymore is because I don't want to mess up this 0. If I do row 3 minus something of this, then this 1 will surely end up changing the 0. So I had already eliminated the x variable. I don't want to introduce it again to the third variable, right? So let's see what happens if you do row 3 minus, let's say, row 1. If I do this, then this becomes 0 minus 1. So then my third row becomes minus 1, and then something here, and then something here. Maybe I get rid of this by doing some multiplier over here, but the x variable gets introduced again. So I'm not going to do that once I've chosen a pivot and gotten rid of the variables here. And so everything below this pivot has now become 0. I'm not going to touch this line. I'm not touch this row and add it to any other rows, because that can mess up this 0. Okay, so that's why we stick with the rows that we have. Okay, I don't really understand why we're subtracting the rows with each other without multiplying. So which multiplication? So I did do multiplication over here, row 2 minus 2 times row 1. Over here I did row 3 minus 3 times row 1. I didn't do any multiplication over here because I didn't need to. It was already, this was minus 4, this was minus 4. If I subtract row 3 from row 2, sorry, row 2 from row 3, I will immediately get a 0. I don't need to do any multiplication over here. In these two cases, I did need to multiply it because the pivot was different from the elements below it. In this case, the pivot was the same as the elements below it. Does that answer your question, Lanya? Okay, perfect. So, did anyone figure out why this is an easy problem to solve? Why I didn't need to solve the system? Can I figure out what combination of these columns I can take to give minus 3, minus 2, minus 5? Let's see if anyone has the answer in the chat. No? Okay. Notice that this right over here, this row, this column is almost the same as this column. The only thing that's different, excuse me, the only thing that is different in column 2 and the right hand side is that the only thing that's different is the signs. So this is 3, 2, 5, and this is minus 3, minus 2, minus 5. Which means that if I just take minus 1, if I take y as minus 1, just negative of this column, and ignore these columns, and the way we ignore this is to set this 2 equals to 0 and this 2 equals to 0, and I immediately get minus 3 minus 2 minus 5, and my solution then becomes 0 minus 1 0. And notice that that's the same solution that we got when we solved this entire system, right? Exactly, Ahmad. It's absolutely right. So that's the idea. I'm looking for some combination of these columns. Of course, I can do this because the solution was so simple. Maybe if one of these values were different, if this was perhaps say minus 4, then I'm in a little bit of a trouble because I need to figure out, because I can't take this minus 1 anymore. I need to find some other values x, y, z that can give me the correct right hand side, right? But for this system, my value of minus 1 works perfectly fine. Okay, so that was the system of, that was the elimination process for 3 by 3 systems. At least when you can do the 3 by 3 elimination, sometimes the 3 by 3 elimination fails. And now let's look at a problem when my elimination fails. And so let's look at this problem. Let's copy this one more time. Excuse me. And so let's put it here. And now let's think of when I will have an issue. I might have an issue when I start doing the first elimination, and so let's put this in matrix form so that I don't need to worry about the variables. So this is 1, 3, 2, minus 3, 2, 2, 2, minus 2, and 3, 5, 6, minus 5, right? That was the system, 3, 5, 6, minus 5, 2, 2, 2, minus 2. Okay. Now, let's think about a system, a different system in which I might have had an issue where I got this second pivot to be 0. If this pivot is 0, I can't really take it to be a pivot. That causes an issue in my elimination because I can't really multiply that with something and add and subtract it from the third row to get 0, right? Because this is the 0. Anything I multiply it by will just give me 0, and so I won't be able to eliminate it in the third equation, right? And so let's look at something like, maybe if this system was not 2y, what if this variable had a coefficient of perhaps 1 times 2, 3, maybe this was 6, right? And now let's try to do the process of elimination. The process of elimination tells me that I do row 2 minus 2 times row 1, okay? And so I carry out this process, 1, 3, 2, minus 3, minus 2, minus 5, and actually let's just do the row 3 minus 3 times row 1 again, right? And so this is 2, so 2 minus 2 times this is 0, 6 minus 2 times 3 is also 0, so I get 0 here, 2 minus 2 times 2 is 2 minus 4, which is minus 2, and then I should have written these values, they're going to change, so minus 2 plus 6 gives me 4. And this one, actually I don't need to do anything about this, this one becomes 0, 0, 2, right? So 0 minus 4, 0, so this is 0 minus 4, I've already done this process, that's the same row, minus 4, 0, and 4. Okay. Now this is a problem because I can't really eliminate y from the third equation because anything I multiply the 0 with is just going to give me a problem. Now at this point our elimination has sort of failed. Elimination fails, but it can be saved. And the reason it can be saved is that there is a non-zero below this equation. And if you think about these rows in terms of equations, there's really no question of order of these equations. If I have to satisfy these equations, there's nothing stopping me from swapping these two equations and saying 3x plus 5y plus 6z equals to minus 5, and write the second equation below it, 2x plus 6y plus 2z equals to minus 2, which means exactly, and at any point I can just switch these two rows together and I get 1, 3, 2. I get the same system but written in a different way. So I switch. Now notice that I have to keep the right hand sides, I have to switch the entire row, I can't switch just these values. So this is 0 minus 4, 0, and this 4 becomes comes over here, and then this you have 0, 0, minus 2, and 4. And now you see that we have a nice little system over here again, where elimination has been saved. There are still 3 pivots. And now I can solve my system. The last equation tells me that minus 2z. See, now I'm putting back the variables now, because this third column referred to z, this column referred to y, and this column referred to x. So this third equation is really telling me, and this was the right hand side, so this is equals to the right hand side, right? And so minus 2z is equals to 4. That's what this third equation is telling me, and I can solve this as z equals to minus 2, plug this value into the second equation, and actually I don't need to do that because this equation is just telling me minus 4y is equals to 4, and I get y equals to minus 1, and now plug both of them. So this is, again, I'm doing back substitution, so x plus 3 times minus 1 plus 2 times minus 2 is equals to minus 3, and you have x minus 3 minus 4 equals to minus 3, which gives me, this is minus 7, goes over there, plus 7, so x is equals to 4. And so my solution is 4 minus 1 minus 2. That's the solution to my problem, x, y, z. So elimination sort of failed here, but we still managed to save it. Okay. Right. Let's look at a case where elimination completely fails. Elimination fails and cannot be saved. And the way that can happen is to first think about how was I able to save it. I was able to save it because when I got a 0 pivot, I could switch it with a row below it which had a non-zero entry in the same column, right? So in the second row I had an equation which had a non-zero entry which gave me a non-zero pivot. But I can't really do that if this second entry was also equals to 0. So in a case where this system, so let's think about how I can get such a system, is when this entry becomes 0, right? And so when does this entry become 0? Let's think about such a system, and maybe I can start off by saying, okay, let's look at this system, let's copy this system, and let's try to make this entry 0 as well, right? Okay, and so let's put this here, and let's ignore this, let's put it here, and let's do this. Okay, and so let me change my system now. I'm changing this to this value to 9, right? And now when you do row 2 minus 2 times row 1, you get this row, and when you do row 3, let's do it and make sure that we're absolutely doing the right thing. So row 3 minus 3 times row 1. So the first entry I get is 3 minus 3 times 1, which is 0. 9 minus 3 times 3, which is 9 minus 9, which is again 0. And 6 minus 3 times 2, which is 0. Okay. And minus 5 minus 2 times 6, right? That's what, sorry, minus 5 minus 3 times 3, which is 4. Okay. And now at this point we have a problem. This last row, firstly, I can't save this elimination process at all because this has created a problem. And what's furthermore problematic is that this equation has already given me a contradiction. This, if you notice what's happening here, this has given me a contradiction. So this equation tells me that 0 times z is equals to 4, which is ridiculous. I can't have any number here which I multiply by 0 to give me a 4. And so this is a contradiction. When you get a contradiction like that, when you get an inconsistent thing, you say that there is no, you can't find any value of z to satisfy this equation. This equation just cannot be satisfied, which means that there is no solution to this system, right? My elimination fails and I just can't do anything over here, right? So this is a point where your elimination fails and you cannot save it, and your solution and your system has no solution, right? Exactly, 0 is not equal to 4. Okay, And so is that so now the question is, does every time my elimination fail I cannot find a solution? Now that's the question that I need to answer. Can I have a solution even if elimination fails? Even if elimination fails. And the answer is yes. The answer is, the reason I didn't get a solution to this system is because I got this contradiction. If I can find a way to avoid this contradiction, then maybe I can find a solution to my system. And the way that I can avoid this contradiction is if this was also 0, because 0 times 0, I know I can put any value of z here and I will get a solution, right? And so let's do that. Let's think of a system. Let's take this system one more time and find a system where I can, so I have this system, I know that I can convert it into this system, and I want to make this last entry as, so I want to make this 0 as well, right? And the way I do this is I change my system. I find a new system, and so let's say I put this as 3, 9, 2, 6. Let's make this minus 9. Okay, and now let's do again the same thing, row 2 minus 2 times row 1, and row 3 minus, row 3 minus 3 times, why is this switching to, okay, 3 times row 1. Okay, and what do I get at this point? I get 0 here, 0 here, 0 here, and at this point I get minus 9 minus 3, so minus 9 minus 3 times minus 3, which gives me a 0. And so this is a 0 here. So this row is now not giving me a contradiction. It's telling me 0 times z is equals to 0. Now how do I interpret that? It's what is this telling me? This is telling me that any value of z satisfies the third equation. And what this really tells me is that I don't have one solution to x, I have infinitely many solutions. But how do I find those infinitely many solutions? And the way we do it is, when you say that any value of z satisfies the third equation, what we're actually saying is that z is a free variable. It's free, it can take any value. Oops, it seems like there is some issue with my pen. I might need to switch the tips. Okay, let's try to work with this for now. Okay, and so what do I get? So let's focus on the first and the second equation. Now the second equation is telling me minus 2 times y is equals to 4. So this is equation 2. And I get y equals to minus 2 from here. And the first equation tells me that x plus 3y plus 2z is equals to minus 3. And I can solve this by saying, okay, I have the value of y, which is x plus 3 times minus 2. But what about z? What value do I take here? And the answer is any value of z. Any value of z. So let's keep z as it is, and let's try to solve x in terms of z. So I get x is equals to minus 3 plus 6 minus 2z. So x is actually 3 minus 2z. So if I want a solution, my solutions are as follows. I have any value of z. I have y equals, so okay, let's write it like this. Let's say I have, what's my solution x, y, z? My solution is I can take any value of z, doesn't matter. For y, I need to take minus 2. And for x, whatever value I take for z, my x will take the value 3 minus 2z, right? So let's try to find a particular solution. So let's say